Hello everyone, welcome back to the online classes. Dear students, in this class now I am going to discuss about circular current loop as a magnetic dipole. The product of the strength of the magnetic dipole and the magnetic length is called magnetic dipole. Here the circular current loop, it acts as a magnetic dipole. Suppose if you are consider this is the circular current loop, and r is the radius of this circular current loop, and at a point P the magnetic field at point P, and the O is the center of this circular loop, and x is the distance between the center of this current carrying circular loop and the point at which the magnetic field is to be calculated. Now I am going to calculate here this circular current loop acts as a magnetic dipole. This acts as a magnetic dipole. In the unit 1 already we have studied electric dipole and electric field. The electric field due to an electric dipole on the axial line. You know that the formula. We know that the equation, the electric field due to an electric dipole at a point on the axial line, that is the electric field due to the axial line, E is equal to 1 divided by 4 5 epsilon naught 2 into Rp divided by R square minus A square whole square. This is equation number 1. This is the expression for electric field due to an electric dipole at a point on the axial line. E is equal to 1 divided by 4 pi epsilon naught 2 Rp divided by R square into A square whole square. Here P is the electric dipole moment and R is the distance between the dipole and the point of observation. But where here R is very greater than A, then A square can be neglected. Then we write this equation, E is equal to 1 divided by 4 5 epsilon naught. E is equal to 1 divided by 4 pi epsilon naught 2p divided by R cube. E is equal to 1 divided by 4 pi epsilon naught 2p divided by R cube. From using these two equations, now we will connect this electrostatics to the magnetism. Magnetic field due to this circular loop at a point on this axial line, already we know that the formula. Now I am going to write directly the final equation. P is equal to mu naught divided by 4 5. B is equal to mu naught divided by 4 5 2 5 into I R square. This is only for one term divided by x square plus all R square whole to the power of 3 by 2. This is equation number 3. Now here in this equation, I is the current in the loop, R is the radius of the loop, and here this x is the distance between the center of this loop and the point of the observation. In this equation also like this, here the x is very greater than R. X is very greater than R, then R square plus x square or x square plus R square, it is nearly equivalent to x square. Then we write this equation, B is equal to mu naught divided by 4 5. P equal to mu naught divided by 4 5 2 5 into I R square divided by R square plus x square, it is nearly equivalent to x square. R square plus x square is equal to nearly equivalent to x square. Now here x square whole to the power of 3 by 2. Here 2 get cancelled, we get only x cube. That is B is equal to mu naught divided by 4 5. B equal to mu naught divided by 4 5, 2 5 I into r square divided by x cube, r square divided by x cube. Here in this equation, we know the formula. Area of the loop A is equal to pi into r square. Area of the loop A is equal to pi into r square. Area of this loop, how to find this area of this loop? That is A is equal to phi r square. Here phi into r square is equal to A. Then we write this equation. B is equal to mu naught divided by 4 5. Then 2i into A divided by x cube. 2i into A divided by x cube. I into A, it is the product of current flowing through the loop and area of the loop. The product of current flowing through the loop and area of the loop is called magnetic dipole moment. In the last class only, I already discussed in the case of torque due to a magnetic dipole. M, this is the magnetic dipole. Magnetic dipole is equal to, it is the product of current flowing through the loop and area of the loop. The product of current flowing through the loop and area of the loop is called magnetic dipole. Hence, the final equation becomes B is equal to mu naught divided by 4 5. B equal to mu naught divided by 4 5, 2m divided by x cube. B is equal to mu naught divided by 4 5, 2m divided by x cube. Here, hence, the current carrying loop behaves as a magnetic dipole. This is the current carrying circular loop. From using this equation, we will write this equation, or this equation is converted into this equation here, which is the expression for the current carrying loop behave as a magnetic dipole. Magnetic dipole means it is the product of current flowing through the loop and area of the loop. Here, the magnetic dipole moment, it is mathematically denoted by the symbol small m. I is the current, A is the area, or the vector form of this magnetic dipole moment is vector m is equal to I into vector A, and its SI unit is ampere meter square. SI unit is ampere meter square, and magnetic dipole moment, it is a vector quantity. Its direction is normal to the plane of that loop, which is the expression for the circular current loop is acts as a magnetic dipole. Now we will make some arrangement or some difference between the electric dipole and magnetic dipole. Now, by making the certain substitutions, the equations for magnetic field due to a magnetic dipole can be obtained from the electric field. We know the definition of the electric field and magnetic field. The region around the electric charge is called electric field. The region around the magnet is called magnetic field, or the region around the current carrying conductor is called magnetic field. Suppose here this is the plus q. This is plus q. Here this is the minus q. The 2 point charges separated by a small distance. Separated by a small distance. This is called electric dipole. This is called electric dipole. That is, P is equal to Q into 2A. This is the midpoint of the electric dipole. This distance is taken as A, and this distance is also taken as A. A plus A is 2A. The product of strength of the either point charge and the distance between the 2 point charge is called, this is dipole moment, electric dipole moment. And magnetic dipole moment means it is the product of current flowing through the loop and area of the loop, or it is the product of, suppose this is the magnet, it has a 2 pole, one is north pole and another one is south pole. The charge at this north pole is, that is denoted by the symbol Qm. The charge at south pole is, that is also denoted by the symbol Qm. Qm means this is the strength of the magnetic pole or charge in the magnetic pole. And this two distance is the distance between north and south pole. This is mathematically denoted by the symbol 2L. Here this is L and L. The distance between the two poles are separated by a small distance. This is taken as a 2L. This is the small difference between the electric dipole and magnetic dipole. Now we will compare the values in case of electrostatics, in case of magnetism. The first one is, this is the dipole moment, physical quantity in case of electrostatics, and is a dipole in case of electrostatics and magnetism. The first quantity is dipole moment. In case of electrostatic, dipole moment equation. Dipole moment, it is mathematically denoted by the symbol P. In case of magnetism, dipole moment, it is mathematically denoted by symbol M. And in case of electrostatic, dipole moment equation becomes, it is the product of Q into 2A. Product of Q into 2A, because here these are the 2-point charges. These 2-point charges separated by a small distance. Here this is the midpoint of this dipole. This distance is, this is A and this is A. A plus A is 2A. These 2-point charges are separated by a small distance. This is called dipole moment. In case of magnetism, this is the magnet. It has two poles. One is north pole and another one is south pole. This total distance is taken as, this is L and L. L plus L is 2L. And the charge in the north pole, that is Qm. Then charge in the south pole is also Qm. And in case of magnetism, dipole moment equation becomes, it is the strength of the either pole, either north pole or south pole. It is the product of strength of the either pole and magnetic length. The product of strength of the either pole and magnetic length is called dipole moment. In case of electrostatic, the product of strength of the either point charge and the distance it is called dipole moment. This is the difference between dipole moment in case of electrostatics and dipole moment in case of magnetism. And the second quantity is field at an axial point. In case of electrostatic, we will derive the expression for the electric field on the axis of a axial line. On the axis of a axial line, then we get the equation E is equal to 1 divided by 4 pi epsilon naught. E equal to 1 divided by 4 pi epsilon naught 2p divided by r cube. E is equal to 1 divided by 4 pi epsilon naught 2p divided by r cube. In case of magnetism, current loop acts as a magnetic dipole. Finally, we get the equation that is also axial point. We get the answer B is equal to mu naught divided by 4 phi. B is equal to mu naught divided by 4 phi into 2m divided by r cube. B is equal to mu naught divided by 4 phi 2m divided by r cube. Here instead of here r cube, we use the x. It is x cube. This is the difference between electrostatics and magnetism. And the next physical quantity is magnetic field at an equatorial point. Magnetic field at an equatorial point. Here the field at an equatorial point is, in case of electrostatic equatorial line, equation becomes E is equal to 1 divided by 4 phi epsilon naught P divided by r cube, which is the expression for the electric field at an equatorial line. Here at the equatorial lines, magnetic field due to the circular loop, you get the equation 2m divided by r cube. But at the equatorial line, we get the only equation B is equal to mu naught divided by 4 phi m divided by r cube. M divided by r cube. There is no 2 pi, only pi for equatorial line. And torque. In case of torque, Torque, it is nothing but twisting force, and it is the product of force and perpendicular distance. In case of electrostatics, torque equation, tau is equal to Pe into sine theta. Tau is equal to Pe into sine theta. In case of magnetism, torque is equal to mb into sine theta. This is the difference between the torque in electrostatics and torque in magnetism. Tau is equal to P into sine theta. Tau is equal to mb into sine theta. Here the P is the electric dipole moment, m is the magnetic dipole moment, E is the electric field, and B is the magnetic field. This is a small difference, and this is the analogy between electric dipole and magnetic dipole. And potential energy due to an electric dipole, we know the equation. Potential energy, it is mathematically denoted by the symbol U. U is equal to minus Pe cos theta. U equal to minus P cos theta. Here in case of magnetism, U is equal to minus, instead of P we use M, instead of E electric field we use B magnetic field. U is equal to minus mb sin theta. There is no difference. Only in case of electrostatic we use magnetic dipole symbol as a P, the electric dipole symbol as a P, and in case of magnetism we use the M is the magnetic dipole as M. In case of electrostatics, electric field is mathematically denoted by the symbol E. In case of magnetism, magnetic field is denoted by the symbol B. And work done. Here, W is equal to Pe into 1 minus cos theta. Pe is equal to 1 minus cos theta. In this case, W is equal to mb into 1 minus cos theta. W is equal to mb into 1 minus cos theta. These are the small difference between, or small analogy between, electrostatics and magnetism. By making all these substitutions, the equation for magnetic field due to a magnetic dipole is obtained due from the electric field due to an electric dipole. Here, from observing all these concepts, here we write the equation Q as a Qm, Q as a Qm, and 2A as a 2L, P as a M, and epsilon naught as a mu naught. This is the only difference. Then 1 divided by 4 pi epsilon naught as a mu naught divided by 4 pi, and instead of electric field we substitute the magnetic field. This is the analogy between the electric dipole and the magnetic dipole. Okay dear students, the next concept of your topic is the magnetic dipole moment of a revolving electron. Magnetic dipole moment means it is a product of current flowing through the loop and area of the loop, or it is the product of strength of the either pole and magnetic length is called magnetic dipole moment. Here, now I am going to discuss about the magnetic dipole moment of a revolving electron. Consider an atom. Here this is the atom. Consider an atom in which an electron of mass me. Suppose if you consider m is the mass of the electron, or me is the mass of the electron, and the charge of the electron is minus 1.6 into 10 to the power of 19 coulomb. Here minus E is the revolving, this is the charge of the electron, and it is revolving around the nucleus of a charge plus Ze. Revolving around the nucleus of a charge plus Ze in anti-clockwise direction. This is atom. It consists of protons, neutrons and electrons, but the protons and neutrons together are called nucleons. This is the central core of the nucleus, and according to the Bohr postulates, the electrons are revolving around the nucleus in a circular orbit. Here this is the minus E is the charge. This charge of the electron is revolving around the nucleus of the charge plus Ze in anti-clockwise direction. According to the Bohr's atomic model, the negatively charged electron revolve around the positively charged nucleus in this circular orbit of the radius. Here r is the radius with the constant speed v. V is the constant speed, and it perform, here the electron is perform uniform circular motion, and when this electron is revolving around the nucleus, it provides the necessary centrifugal force on these electrons. But in between these two charges, here this is also charged and this is also charged, in between these 2 point charges there is a Coulomb's electrostatic force of attraction between the electron and the nucleus. This uniform circular motion of the electron, here due to this electron, when this electron is moving in the circular path, the electric current is produced in the anti-clockwise direction. In the anti-clockwise direction. Here in this condition, when the electron is revolving around the nucleus in a circular orbit, then here t is the time period of revolution of electron. T is the time period of revolution of electron. T is the time period of revolution of electron. When this electron is revolving around the nucleus in a circular orbit, then the area of the circular loop A is equal to pi into r square. Here the electron is revolving around the nucleus in a circular orbit with the constant speed. The product of the mass of the electron with the speed of the electron and radius of the electron, it is the angular momentum. In first PUC, in case of system of particle and motion in a plane topic, already we use this term. L is, it is mathematically denoted by the symbol angular momentum, small l or capital L. L is equal to me into v into r, mass of the electron, speed, and this is radius, angular momentum of the electron. Then the speed of the electron, you know the formula, speed of the electron. How to calculate the speed? In this case, this is the speed of the electron. Speed, it is mathematically denoted by the symbol v. Speed is equal to total distance travel, or speed is equal to distance divided by time. Speed is equal to distance divided by time. Then time is equal to distance divided by speed. Time is equal to distance divided by speed. And this electron is revolving around the nucleus in a circular orbit. The distance covered by this electron is, that is the circumference of the circle, 2 pi r. Circumference of the circle 2 pi r divided by its speed is v. Divided by the speed is v. When this electron is revolving around the nucleus in a circular orbit, due to Coulomb's electrostatic force between this electron and nucleus, here the Coulomb's electrostatic force, due to this force, the current due to the motion of the electron, here the current is produced because the rate of flow of charge is called current. Current due to motion of the electron. Current due to motion of the electron is, current due to the motion of the electron is, that is I is equal to E divided by T. Current due to motion of the electron is I is equal to E divided by T. E divided by T means Q by T. Q is the charge, there's the charge of the electron is E. I is equal to E divided by T. Now substitute the values. Here T is equal to 2 pi r divided by V. T is equal to 2 pi r divided by V. Substitute this T value in this equation. We get EV divided by 2 pi r. I is equal to EV divided by 2 pi r. Because ಇಲ್ಲಿ ನಮಗೆ I value ಯಾಕೆ ಬೇಕಾಗಿದೆ? Magnetic dipole moment. Magnetic dipole moment M is equal to, it is the product of current flowing through the loop and area of the loop. Now you get I is equal to ev divided by 2 phi r. This is equation number 1. And the magnetic moment it is associated with revolving electron. Magnetic moment is associated with a revolving electron. Actually the magnetic moment, it is mathematically denoted by the symbol small m, or when it is associated with the revolving electron with the angular momentum, then we write this equation mu l. The magnetic moment is associated with the electron when it is revolving around the nucleus in a circular orbit. Mu l is equal to, it is the product of current flowing through the loop and area of the loop. The product of current flowing through the loop and area of the loop. Mu l is equal to I into A. Mu l is equal to I into A. Here I is equal to equation EV divided by 2 pi r. Remember this equation. The current due to the motion of the electron is I is equal to EV divided by 2 phi r, and magnetic moment associated with the revolving electron mu l is equal to I into A. And here the mu l is equal to I into A equation here. Mu l is equal to I into A. Substitute the values. Mu l is equal to I. Mu l is equal to I. I means current due to the motion of the electron. Substitute the I value here. Mu l is equal to EV divided by 2 pi r. EV divided by 2 phi r into A. Mu l is equal to EV divided by 2 phi r into A. Then mu l is equal to EV divided by 2 phi r into A. A is the area of the circle, that is phi into r square. Pi into r square, here pi and phi cancel, r and r square is cancel. Then mu l is equal to EV divided by, mu l is equal to EV divided by, or mu l is equal to EV into r divided by 2. Mu l is equal to EV into r divided by 2. This is equation number 2. Now we want to calculate this value. Mu l is equal to EV r divided by 2. Here, due to this electron, the magnetic moment is produced. That's why mu l is equal to EV into r. You know the formula, the angular momentum L is equal to mvr. Here there is no m value. That's why multiplying and dividing by the mass of the electron, we get the value. The magnetic moment associated with the revolving electron mu l is equal to me into v into r into e divided by 2 into me. Mu l is equal to me into v into r into e. Here v into r into me divided by 2 into me. Now I can write this equation. Mu l is equal to L into E divided by 2 into me. L into E divided by 2 into me, or mu l is equal to E divided by 2 into me. Mu l is equal to E divided by 2 into me into angular momentum L. This is equation number 3. Here L is equal to me into v into r. This is the angular momentum of the electron. We get the equation mu l is equal to E divided by 2 me into L. L is the angular momentum of the electron. In vector form, we can write this equation. The magnetic moment associated with the revolving electron mu l is equal to minus E divided by 2me minus E divided by 2me into vector L, which is the vector form of the magnetic moment associated with the electron or revolving electron. In this equation here, this negative sign indicates the angular momentum of the electron is opposite in the direction of magnetic field. If the charge is positive, then the momentum and the magnetic moment are in the same direction. or in the same direction. Therefore, here the ratio of, from using equation number 3, now I can write this equation from using this equation. The ratio of the magnetic moment associated with the revolving electron divided by the angular momentum mu L divided by L is equal to E divided by 2me. Mu L divided by L is equal to E divided by 2me. This ratio of magnetic moment of the angular momentum, magnetic moment to the angular momentum, this is called gyromagnetic ratio, and it is the constant value. This is called gyromagnetic ratio. The ratio of magnetic moment, mu L is the magnetic moment or magnetic moment associated with the revolving electron to the angular momentum. The ratio of magnetic moment to the angular momentum, it is called gyromagnetic ratio. It is called gyromagnetic ratio. ಏನಂತ ಕರಿತೀವಿ ನಾವು ಇದನ್ನ gyromagnetic ratio ಅಂತ ಕರಿತೀವಿ, and it is always constant value. Gyromagnetic ratio, the definition of gyromagnetic ratio is, it is the ratio of magnetic moment to the angular momentum. The ratio of magnetic moment to the angular momentum is called gyromagnetic ratio. Now we will find the value of gyromagnetic ratio. The ratio is, that is mu L. Gyromagnetic ratio definition is mu L divided by L, the ratio of magnetic moment to the angular momentum. The ratio of magnetic moment to the angular momentum is called gyromagnetic ratio. That equation is E divided by 2 into me. But from Bohr's second postulate, or from Bohr's quantization rule, from Bohr's quantization rule, you know the Bohr's second postulate. Bohr's second postulate is the angular momentum of an electron is equal to integral multiple of nh divided by 2 phi. You know that equation, L is equal to nh divided by 2 phi, or it is also equal to mvr, or mass of the electron into mv into r is equal to nh divided by 2 phi. From this Bohr quantization condition, here n is equal to 1, 2 and 3, so on up to, it is the number, and h is the Planck's constant. Planck's constant value is 6.626 into 10 to the power of minus 34 joule second. From using this Bohr quantization rule, the angular momentum of an electron is equal to integral multiple of nh divided by 2 phi. Then here mu L equation becomes mu L is equal to here it is mu L is equal to E divided by 2 into mv. Here this value becomes here into L is equal to, L is, that is nh divided by 2 phi, nh divided by 2 phi. Here E divided by 2me into nh divided by 2 phi. For minimum value, here n is equal to 1. For minimum value n is equal to 1, then mu L for minimum, or magnetic moment for minimum, it is equal to E into h, n equal to 1 divided by 2 into 2 is 4 phi into me. Mu L for minimum is equal to EH divided by 4 phi into me. This minimum value of magnetic moment associated with the electron is called, this is called Bohr magneton. It is called Bohr magneton. Gyromagnetic ratio means the ratio of magnetic moment to the angular momentum. The ratio of magnetic moment to the angular momentum is called gyromagnetic ratio. And Bohr magneton means this minimum value, this is called Bohr magneton. Mu L into minimum is equal to EH divided by 4 phi into me. This is the very important for your examination. ಇದು 5 ಮಾರ್ಕ್ಸಿನ ಕ್ವೆಶ್ಚನ್. ನಿಮಗೆ derive an expression for the Bohr magneton anta kelabodu, or derive an expression for the magnetic dipole moment of a revolving electron antanu kuda kelabodu. Mu L is equal to EH divided by 45 into mv. Now I am going to calculate what is the exact value of the gyromagnetic ratio and estimation of Bohr magneton. Here, the first one is gyromagnetic ratio for an electron. Gyromagnetic ratio for an electron. Gyromagnetic ratio, it is defined as the ratio of magnetic moment to the angular momentum is called gyromagnetic ratio, E divided by 2 into mv. Now mu L divided by L is equal to E is value, that is 1.6 into 10 to the power of minus 19 divided by 2 into the mass of the electron. It is the constant value. The mass of the electron is 9.1 into 10 to the power of minus 31 kg. 9.1 into 10 to the power of minus 31 kg. E is equal to 1.6 into 10 to the power of minus 19 coulomb divided by 2 into 10 to the power 2 into 9.1 into 10 to the power of minus 31. Here 1.6 into 10 to the power of minus 19 divided by 2 into 9.1. 2 into 9.1, that is 18.2 into 10 to the power of minus 31. Then 1.6 divided by 18.2 is equal to 1.6 divided by 18.2 is, that is 0.0879 into 10 to the power of minus 19 plus 31. 10 to the power of minus 19 plus 31, you get the equation 12, or directly you can write here mu L divided by L is equal to there 8.79, or nearly it is about 8.8 into 10 to the power of 10. Actually minus 19 plus 31, you get the equation 12. Rearrange this value, we get 8.8. Here this is 0.11 and here 10. 8.8 into 10 to the power of 10. Here the SI unit of this gyromagnetic ratio is, this is coulomb per kg. Coulomb per kg, because the SI unit of charge is coulomb, the SI unit of mass is kg. This is coulomb per kg, which is the value of gyromagnetic ratio mu L divided by L. The ratio of magnetic moment to the angular momentum is called gyromagnetic ratio. You know this equation, E divided by 2 mv. E value is 1.6 into 10 to the power of minus 19, and mass of the electron is 9.1 into, this is the charge of the electron, this is the mass of the electron, don't confuse, only E. This is the charge of the electron, this is mass of the electron. When you are substitute these two values in this equation, finally we get the answer. Mu L divided by L is equal to 8.8 into 10 to the power of 10 coulomb per kg. This is also one mark question. ನಿಮ್ಮ annual examination ಅಲ್ಲಿ ಕೇಳ್ತಾರೆ, write the value of gyromagnetic ratio. The value is 8.8 into 10 to the power of 10 coulomb per kg. Next, I am going to calculate the estimation of Bohr magneton. Estimation of Bohr magneton, that is second point. Estimation of Bohr magneton. Estimation of Bohr magneton. Mu L for minimum. This is the Bohr magneton. Final equation of the derivation. Mu L for minimum value EH divided by 4/5 into ME. This is Bohr magneton. Bohr magneton means it is the minimum value of magnetic moment associated with that electron. Mu L for minimum value is EH divided by 4/5 into ME. Substitute the values here. E is 1.6 into 10 to the power of minus 19 into H is the Planck's constant, that is 6.626, or directly you can write 6.63. 6.626 into 10 to the power of minus 34 divided by 4 into 5 value is 22/7 or 3.14 into the mass of the electron is, that is 9 point, the mass of the electron is here the 9.11 into 10 to the power of minus 31. E is the charge of the electron, H is the Planck's constant, the SI unit of charge is coulomb, the SI unit of Planck's constant is joule second, electron is kg, the SI unit of electron is kg. Now we will multiply the values. 1.6 into 6.626, 6.626, we get the values 10.6016 into 10 to the power of minus 19 and minus 34, that is 10 to the power of minus 53 divided by 4 into 3.14 into 9.11, that value is become 114.4216 into 10 to the power of minus 31, dividing these two values. 10.6016 divided by 114.4216, we get the answer, that is 0.0926 into 10 to the power of minus 53 plus 31, minus 53 plus 31, 0.0926 into 10 to the power of minus 53 plus 31, that is 10 to the power of minus 22, 0.0926 10 to the power of minus 22, or μL for minimum value. Here it is the estimation of Bohr magneton value is, that is 9.26 into 10 to the power of minus 24. 9.26 into 10 to the power of minus 24 ampere meter square. Ampere meter square. The SI unit of magnetic dipole or magnetic dipole moment is ampere meter square. You get the values 9.26 into 10 to the power of minus 24 ampere meter square, which is the value of the estimation of Bohr magneton. Thank you.